Hey, today I will briefly discuss Minkowski sums and how we can use this type of summation approach in robot motion planning, especially to determine the free space in our 2D environment. And again, as in the case of previous approach, the consolidated approach, we will be using polygonal type of robots, and there will be this time a difference between the workspace and the configuration space. They will not be exactly the same since the robot will be polygonal, not a point type robot. So we need to find a way to determine this free space properly. And we'll assuming that all the obstacles in the environment and the robot are all convex type of polygons. We will denote the free obstacle space of P, the obstacle, let's say, space of P by CP. It is represented with such a mathematical expression. It's actually the robot, the intersection of the robot with the obstacle. So the P is our obstacle, R is the robot. So the intersection, their intersection, if the intersection is not empty, then that field, that points will be referring to the C obstacle of P, or renamed as CP. Here you see this, let's say, larger polygon is actually representing CP since we have the intersection of the robot with the obstacle. But the outer, if you move this, let's say, robot to the right a little bit, then we will say that there will be no intersection between the robot and the obstacle, and that will not be satisfied since the intersection will be an empty set. So in summary, the intersection of the robot with the obstacle defines actually C obstacle of our given obstacle P. And we will be defining this field, this region, actually CP, by making use of Minkowski sums. But before we discuss how we do that, let's briefly go through the details of Minkowski sums. It's not complicated, as you see. This is how we represent the summation operation between two sets, S1 and S2. They are all two-dimensional. They are submembers of two-dimensional field. And that's a very simple operation. The items inside, that's the members in S1 first set and the second set should be summed together. And this will give us the Minkowski sum, the resulting Minkowski sum. And it's a kind of a vector summation. So if P is represented with X and Y coordinates and Q is also represented with a similar approach, then what we are going to do, we will sum X coordinates and then write the result into the X value and do the same also for the Y coordinate. Here's an example, actually, the summation. This is the Minkowski sum of S1 and S2. This is not CP or the obstacles space of the robot. It's not a robot, but if you are doing Minkowski sum, it's simply actually moving the center of this, let's say S2, over the boundaries of S1. So if you do it, then the resulting, the covered region actually will give you the Minkowski sum of S1 and S2. For instance, think about S2 here. Let me draw it if I can properly. Yes. That is the center of S2 here, and as you see, this part is covered. And if you again draw another one, for instance, here, while you are moving the S2 on the boundaries of S1, that will be the covered area while we make this movement. So this movement will give you the Minkowski sum of these two, let's say, polygons, convex polygons. This is another example. We have much simpler shapes, a circle and a rectangle. Again, if you move this box over the circle or circle over the rectangle, you will obtain this summation. So what about the CP, or the obstacle space of our configuration space of our obstacle P? It's actually the Minkowski sum of our obstacle with the negative of our robot. This is an important parameter here, an important sign. We are negating our robot and then doing the Minkowski sum to determine the configuration space of our, let's say, obstacle. So our robot shouldn't be actually moving inside this space, otherwise there will be collisions. Now let's focus on specific property of Minkowski sums. Assuming that we have two objects, P and R, in the plane, and if CP is again equal to, this time, this is nothing related to the previous theorem, it's another observation. If you take the Minkowski sum of these objects, then there might be an extreme point in the direction. I'm sorry. There might be an points in the extreme point in the direction D, and that will be actually the sum of extreme points of P and R in the direction D. You'll see an example about it. So this is P, our first object, R, our second object, and if this is your vector D, and if you want to determine the extreme value of your resulting summation without doing any more computation, what you can do, you can simply determine the extreme point of R, which is here, this small r. So in this direction, we have a maximum value at this point. And regarding P, again, we have this maximum extreme point, small p. So if you want to determine the extreme point in this direction of your Minkowski sum, you can simply sum these two values, P and R, together to determine this extreme points in the Minkowski sum. Now we have another theorem, not more complicated. Again, we have two objects, P and R. They are convex polygons. They have n and m number of edges. N is the number of edges of P, and R has m number of edges. Then the Minkowski sum, P and R, is again a convex polygon, and at most, in maximum, they can have n plus m number of edges. Now let's have another definition. This is about pair of pseudodisks. This is an important definition while we are doing some computations related to Minkowski sum. Here you see the example of a pair of pseudodisks, but here you see that this pair is not pseudodisk. What is a pseudodisk? If the boundaries of this pair are intersecting at only 2 points, then we can say that they are a pair of pseudodisks. But if they intersect more than 2 points, then we cannot name them as pseudodisks. Instead, we will simply say that they're not an example of pseudodisks. So we have another observation regarding these. If you have a pair of polygonal pseudodisks P and P prime, they will be crossing over just twice, not more than that. So this is very similar to the previous explanations. We have another observation. It's about the extreme regions. So now we are assuming that there are two polygons, convex polygons, P1, P2, and we are assuming that they have disjoint interior. So they are independent items, objects in the field. Then we have two directions, D1 and D2. And in these directions, P1 is more extreme than our second object, P2. Then if this is defined, this is assumed, then either P1 is more extreme than P2 in all the directions in the range from D1 to D2, or it's more extreme in all directions in the range, in the reverse direction from D2 to D1. Now we will see a sketch about it. This is actually the thing. We have two objects, P1, P2. They are disjoint, they don't have any intersection, and they have some, let's say you have some extreme directions, D1, D2, and D3. So now what we have done, we have divided the, let's say, circle, this region into three fields. Let's say first field, second, and the third field. In the first region, we have P1 as the extreme, let's say, object. So in this range, if your direction vector is in this range, then we can say that P1 will have more extreme. But if your direction vector is in this range, then P2 will be more extreme. But if your direction vector is in between these points, then we will say that they will have the same extreme values. They are equally extreme in this range of, let's say, circle. P1 and P2 are the same. We have another theorem. Again, we are assuming that the two objects P1 and P2 are convex polygons having disjoint interior. And now we have an additional object, which is R. So if you take the Minkowski sums, P1 and R, another Minkowski sum between P2 and R, then we can say that these are pseudodisks. So what is that? The Minkowski sum of the first obstacle with the robot, let's say R, and the Minkowski sum of the second obstacle with the robot R will be kind of an pseudodisk, which means that they will be crossing over just 2 points. So this is the crossings, and we can say that they are pseudodisks. We have another theorem, not much important as the other ones. We have a collection of convex polygons, convex polygon pseudodisks with n number of edges in total. Then the complexity of their union operation is at most 2n. So in maximum, we can have 2n number of edges if you try to union all these pseudodisks together. Here is the actually pseudocode of the Minkowski sum of two objects, P and R. P, as you see, is again, here's the details of the P are defined. P has vertices starting from V1 to Vn, and then R again is a convex polygon. Its vertices starting from W1 to Wn, and we will be assuming that these are ordered in counterclockwise direction, and the first vertices will be the ones actually having smallest y coordinate. If they have the same, let's say if V1 and V2 has the same y coordinate and has the smallest one, then you can check this one actually having the smallest x coordinate, if that's the case. And then the result of this algorithm is obviously the Minkowski sum of two convex polygons, P and R. This is the main algorithm to determine the Minkowski sum of the given objects. What we do, we have a kind of an indices for P and R. For P, we use the index, the term I, and for R, we use the term J. And then we have some initialization here. We add two extra, let's say, vertices to the end of the set. Again, it's done for the robot R here. The first two are added also to the end of the set, the set of vertices in the counterclockwise direction. Then here we do actually we have a kind of a loop here, but this loop, as you see, just running once. But in this operations, Sometimes we are increasing the index I, or sometimes we may increasing J, or sometimes both are increased. So here we are actually trying to determine the vertices of the resulting Minkowski sum. So since if you determine these vertices in maximum direction, in extreme directions, then you'll be done with the Minkowski sum. Otherwise, determination of this Minkowski sum is quite difficult. That's why we make use of the vertices in the extreme directions, and we check actually the angles all the time, depending on whether I is larger or J is larger, which means that P has some extreme values or R has some extreme, let's say, values in that direction. We do the summation accordingly and store these vertices, the resulting vertices, into our resulting Minkowski sum. And that will be the final polygon, which is the Minkowski sum of P and R. So as I said, we have a single loop. In that loop, we are sometimes increasing either I or J. So we can say that in linear time, you can determine the summation of these two objects. And as I've done on the example, any vertex of the resulting Minkowski summation is actually the sum of the vertices of the P and R in the extreme directions. And this is the overall theorem. The Minkowski sum of our two convex polygons with n and m vertices can be computed in maximum n plus m linear time. So the time complexity depends on the number of vertices our actually objects have. This theorem is actually continuation of the previous theorem. Again, it's about time complexities. We have PNR polygons. They have n and m number of vertices. Then the complexity of our summation is bounded by the followings. If you are using convex polygons, then this is theorem 10. But if one of them is convex and the other one is non-convex, then the complexity is actually depending on the multiplication of the number of vertices of these two polygons. But if both of them are non-convex polygons, then the complexity is much more. We have n squared times m squared, which might be very time consuming. So that's why we always prefer to work with convex polygons. Things will be much easier in shorter time. You can complete, you can do the computation. So how are we going to use this in the motion plans of the robots? We have some theorems about, but they're not complicated. Let's have a look at the first one. Again, assuming that R is our convex robot having constant complexity, which means that it's not changing in shape. It's moving just in X and Y directions. And again, we have some number of obstacles which are not intersecting. And in maximum, these obstacles have n number of edges. Then the complexity of our free configuration space will be depending on the number of edges these obstacles have. So it's simply O of n. So the free configuration space of our robot R and set of obstacles S is depending on the number of edges these obstacles have. So now what we are going to do, if you somehow determine the free space, construct the free space, then we can follow the same actually approach we have done in the trapezoidal map. Things will be completed. But instead of completing the free space, what we are going to do is quite easy to determine the forbidden space. And this forbidden space is related to the Minkowski sums of the obstacles. If you determine this forbidden space, then you can simply take the complement of it and from the bounding box and determine the free space where your robot actually can move. So this is how we determine the forbidden space. So we take the Minkowski sum of the obstacles with the negative of our robot, and if you take the union of them, then you will determine the forbidden space. And later, if you take the difference of your forbidden space from your bounding box, then you will determine the free space. So this is how we determine the forbidden space. We have the forbidden space of the, let's say, the configuration spaces of the obstacles, which are determined by Minkowski sums. If you have them, then you can simply join them together to determine your resulting forbidden space. And the time complexity of this operation is a bit complicated. N times logarithm square of n. It's coming from the triangulations. In this approach, we need to have a triangulation, and also we have a kind of a binary merge and sort algorithm. If you look at here, we divide the space into two parts from P1 to n over 2, and the other half is here. So it's very similar to merge and sort algorithms. That's why our time complexity is a bit higher, which is n times logarithm square of n. So once you determine the free forbidden space, then you can easily determine free space by subtracting it from the bounding box. And later, as we have done in the previous approach, you can construct the trapezoidal map in this free space, in this, let's say, bounding box, determine the road map, and finally do a kind of a breadth-first search to determine your path from the starting point to the goal point. So we're not going to discuss the other details. As you see, sometimes we might have such an intersection, although at the beginning of the problem, we didn't have any, let's say, intersection between the obstacles. Their Minkowski sums might be intersecting, as it is the case here. And again, we have two crossings, which means that these Minkowski sums are pseudodisk, and things will be much easier for us. We can easily do the computation and determine this path from the starting point to the goal point. So that is actually summarizing the time complexity. So again, if you have your robot R in the environment and set of obstacles again in the environment having n number of edges, then you can pre-process this field, this two-dimensional field composed of some obstacles in n times logarithm square of n in expected time. Then the things are not complicated. The path can be computed in linear time, which depends on the number of edges your obstacles have. But if you are using the same, let's say, obstacles for another problem, again, you don't need to use this part. You don't need to do this computation. You can simply say that the path can be computed in linear time. But if you, let's say, introduce new obstacles into your environment, then you need to do this computation once again, and it will cost you some time.